Okay, in this lecture we're going to conclude our section 3.8 material on forced vibrations, or modeling a mass spring system which has some sort of external force being applied. Now in the previous lecture we were considering the case of undamped forced vibrations. So now we'll move on to the case of damped forced vibrations. And let's consider an example of this. So here in this example, we have a mass which weighs 8 pounds, stretches a spring 0.8 feet, and this mass is attached to a dashpot mechanism that has a damping coefficient of 1 pound-second per foot and is acted on by an external force of 2 cosine of 2t pounds. So if this mass is set in motion from its equilibrium position with no initial velocity, we're asked to find the position y of the mass at time t and identify the transient and steady state solutions. Then we're told to plot the displacement, transient solution, and steady state solution versus time. And finally, we're asked what is the resonance frequency for this system. So as with any of these mass spring problems, the first thing that we need to decide on is a unit of measurement for our displacement. And reading through the problem, several of our units were given in terms of feet, so let's stick with that unit. I'll say, let us measure our displacement in feet. So we know that our equation of motion in general is given by my double prime plus by prime plus ky is equal to capital F of t, our external forcing function. And so let's see if we can find these different constants. So to get our mass, well, we're told how much this mass weighs. And to get the mass itself, we would take the weight of our mass and divide through by the acceleration due to gravity. We know force is mass times acceleration, so the force that would be needed to move our mass, which is equivalent to its weight, would be the mass times acceleration due to gravity. So solving for m, we have a weight of 8 pounds. And for g, if we're measuring in feet, we would use a value of 32 feet per second squared, which gives us a mass of 1/4 slug. Now in the problem statement, we were given the damping coefficient was 1 pound-second per foot. And then finally, to find the stiffness K, we could make use of Hooke's law. So the force needed to stretch our spring was equivalent to the mass's weight of 8 pounds. And then we would divide by the displacement of our spring. We were told here that we stretched 0.8 feet. So we're left with a stiffness of 10 pounds per foot. So substituting these expressions into our equation of motion, we have the mass, which was 1/4 y double prime, plus b, which is 1 y prime, plus 10y is equal to the external force, which we were given in the problem, as 2 cosine of 2t pounds. Or putting this in standard form, if we multiply everything by 4, we have y double prime plus 4y prime plus 40y is equal to 8 cosine of 2t. And we had initial conditions, y prime and y at time 0 are both 0, since this mass was set in motion from its equilibrium position with no initial velocity. So to solve this equation, well, we have a non-homogeneous second-order linear equation. So let's first look at the homogeneous equation. Let us consider y double prime plus 4y prime plus 40y is equal to 0. And to solve, we would look for solutions of the form y equals e to the rt power, so that r is a root of the characteristic equation, r squared plus 4r plus 40 is equal to 0. And if we make use of the quadratic formula to solve for r, we find that r is given by -4 plus or minus the square root of 4 squared, which would be 16, minus 4 times 1 times 40, which gives us 160, all over 2 times 1. So this gives us a -4 plus or minus the square root of -144, which would be 12i, all over 2. So dividing through by 2, we have roots of -2 plus or minus 6i, complex conjugate roots, which means that our homogeneous solution, or what we call the transient solution for a mass spring system, is given by C1 e to the -2t cosine of 6t plus C2 e to the -2t sine of 6t. Now our next step is to find a particular solution of the non-homogeneous equation. So let's make use of the method of undetermined coefficients. We see that our forcing function on the right-hand side is a constant times cosine of 2t. And so let's consider a particular solution of the same form. Y of t is equal to some constant a times sine of 2t plus b times cosine of 2t. And we need to find our first two derivatives of this function to substitute into our non-homogeneous equation. So we find here that y prime would be 2a cosine of 2t minus 2b sine of 2t, and y double prime would be -4a sine of 2t minus 4b cosine of 2t. And now let's substitute into our non-homogeneous equation. We're looking for y double prime plus 4y prime plus 40 times y, which has to equal 8 cosine of 2t. And so let's see what we have when we substitute y and its derivatives into this equation and group like terms. So let me look at what I have if I group all of the sine of 2t terms together. When I have y double prime plus 40 times y, that gives me a 36a times sine of 2t. And then for the 4y prime term, I have a -8b sine of 2t. And then grouping my cosine of 2t terms, when I add my y double prime plus 40 times y, I have a 36b times cosine of 2t. And then from the 4y prime term, I have 8a times cosine of 2t. So grouping these like terms, we have the following, and this has to equal our 8 cosine of 2t. So equating the coefficients, we have 36a minus 8b has to be 0, and 8a plus 36b has to equal 8. So let's continue our work on to the next page. If we divide each of these equations by 4, I would have my first equation would be 9a minus 2b is equal to 0. And the second equation, if we divide by 4, is 2a plus 9b is equal to 2. So from the first equation, it follows that a is 2/9 of b. And so if I substitute that into the second equation, we get 4/9 b plus 9b is equal to 2. Therefore, summing these values, we have 81 plus 4 would be 85/9 b is 2. And so b is 18 over 85. And so substituting this back into my a equation, I find that a is 2/9 of b, which would give me 4 over 85. So we find that our particular solution, capital Y, is given by 4 over 85 sine of 2t plus b, which was 18 over 85 cosine of 2t. And so our general solution, y of t, would be the sum of our homogeneous solution, which was c1 e to the negative 2t cosine of 6t, plus c2 e to the negative 2t sine of 6t, plus my particular solution, which was 4 over 85 sine of 2t, plus 18 over 85 cosine of 2t. And to finish out the problem, we need to solve for the constants, c1 and c2, using the initial conditions, which means that I need to find the first derivative of this general solution. So differentiating y prime, making use of the product and chain rules, I have a negative 2c1 e to the negative 2t cosine of 6t minus 6c1 e to the negative 2t sine of 6t, then minus 2c2 e to the negative 2t sine of 6t, plus 6c2 e to the negative 2t cosine of 6t. And then moving to the derivative of my particular solution, I would have 8 over 85 cosine of 2t minus 36 over 85 sine of 2t. So let's apply our initial conditions. If we substitute 0 into the general solution, we are left with c1 plus 18 over 85, which had to be 0 since our mass was set in motion from its equilibrium. And this gives us C1 is equal to negative 18 over 85. And now substituting 0 into the derivative of our general solution, we are left with negative 2C1, which would be a positive 36 over 85, plus 6C2, plus an 8 over 85, which had to equal 0. So it follows that 6C2 is equal to negative 44 over 85. And then dividing through by 6, we get C2 is negative 22 over 255. So substituting these expressions back into our general solution, we find that y of t is given by our homogeneous solution. So we have C1, which is negative 18 over 85, e to the negative 2t cosine of 6t, plus C2, which is negative 22 over 255, e to the negative 2t sine of 6t, plus my particular solution, which was 4 over 85 sine of 2t, plus 18 over 85 cosine of 2t. So this is our solution of this initial value problem describing the motion of our mass. And we were asked to identify the transient and steady state solutions. So recall the transient solution is what we call the homogeneous solution. And the particular solution is what we call the steady state solution. So here we see that as t increases, as t becomes larger, our transient solution will decay to 0. So this is why we call it transient. After a large enough time goes by, this transient solution becomes negligible. And our steady state solution is going to oscillate with a fixed amplitude. Now in the problem statement, we were asked to plot the transient solution, steady state solution, and our displacement on the same graph. So I've given that here in the notes in this figure. The transient solution is plotted in blue, and we can see that as t increases, that transient solution will decay to 0. The steady state solution is plotted with the red dashed line, and the displacement is plotted in black, which is the sum of my transient and steady state solution. So what we see here is that as time increases, eventually our displacement matches up with the steady state solution because our transient solution approaches 0. And then for the very last part of this problem, we were asked for the resonance frequency of this system. So what would be the frequency of the external forcing function that would produce the largest amplitude response for my steady state solution. So in the first part of this section, we had derived a formula for the resonance frequency. So here, let me say the resonance frequency is given by what we call gamma R, and it was given by the square root of k over m minus b squared over 2m squared. So substituting in the values that we had, we find the square root of our stiffness, which was 10, divided by the mass, which was 1/4, minus the stiffness, my damping coefficient B, which was 1 squared, over 2 times the mass squared. And so this simplifies to the square root of 32, or 4 times the square root of 2. So in order to see the largest amplitude in my steady state solution, I would want to apply a forcing function whose frequency is 4√2.